it. Okay, so let's see. So yesterday we turned our original question on its head, and we started to ask ourselves, well, if we state what labels are invariant, can we specify a group? And if you remember, yesterday we considered two types of invariance. So we said, well, maybe we would like this quantity to be invariant. And if we wanted that quantity to be invariant under our transformations, we found out the group that left this quantity invariant was OD. And then we said, so this is a D over here. And then we said, well, let's supplement that by one extra condition. So if our invariants are the sum from I is equal to 1 to D of VI, WI, and this quantity. So I'm not writing down the sums, but of course these repeated indices are to be summed. There are D of them. And now I contract this with any D vectors. So if I say I would like both of these to be invariant, the group that I've specified here is SOD. Okay? And it was this group that was related to what Jim was saying yesterday in his supersymmetry lectures. Okay. Now, what's the most natural thing we could do? So what we've considered there are real vectors. So we could decide now to start considering complex vectors. So we're going to change our invariance, and we're now going to say that we would like the following quantity to be invariant. So that was yesterday. What happens if we want the sum from I is equal to 1 to D of VI, WI complex conjugate to be invariant? If we're taking the complex conjugate here, it means that we are now considering vectors whose components need not be real. They can be complex. So the transformation that I'm going to consider, I'm going to imagine that VI is allowed to go into UIJ, VJ, and in fact, U need not be a real matrix now. Okay? It is now allowed to have complex entries. So again, if I write this with bracket notation, this would be WV, and my transformation law would be V goes into U times by V. In this case, to get the bra from the ket, I need to transpose and I need to complex conjugate. So I need to do the Hermitian conjugate. So if I want to figure out, this is the transformation rule for ket V. If I want the transformation rule for bra V, I need to complex conjugate and transpose this equation. So what it will become, I shouldn't write equals, I should say goes into, the transformation law for bra V would be that. Okay? Everybody happy with that? Now, what is then the condition that my invariant is invariant? Well, I need WV. This will go into W, U dagger. So there I've got the transformation rule for bra W. There's the transformation rule for ket V. And I want this to be invariant. So I would like this to stay WV. Once again, I'm going to write this as W, the identity on V. Now, I again say, well, I would like this relation to hold for any vector W and for any vector V. In particular, W and V can range over a complete basis. And that means that, in fact, I'm not looking at an equality between matrix elements. I'm looking at an equality between matrices. So I learn, in fact, that my condition is that u dagger u should be equal to 1. Okay? In exactly the same way that we saw requiring that matrices are orthogonal is consistent with closure, you can check that unitarity is consistent with closure. So let's imagine we have u1 dagger u1 is equal to the identity, and u2 dagger u2 is equal to the identity. So u1 is unitary, u2 is unitary. The question we ask ourselves, if we want closure, is would u1, u2 be unitary? Well, let's check that. So we can calculate u1, u2 dagger times by u1, u2. What is this equal to? Well, when I want to take the Hermitian conjugate of a product like that, I swap the order of the factors and I dagger each factor. So I would get u2 dagger, u1 dagger, u1, u2. Well, those two collapse to give me the identity. So I've now just got u2 dagger u2, and that collapses to give me the identity. So yes, this is consistent with closure. So I'm again going to get some sort of a matrix group here. The matrix group that I get, I call UD. D tells me I'm dealing with D by D matrices. And U tells me they are unitary. Okay. So now what do? Well, when we've got a continuous group like this, we always try to check what do the generators look like. So let's see what the generators would, what properties would they have to have. So we can set U equal to e to the I alpha times by the generator. Let's now calculate U dagger. So if we take the dagger of this, so U dagger would be equal to. So it's going to change the I into a minus I. So we'll get e to the minus I, we'll have an alpha, and we will have a t dagger. T gets daggered. And the unitarity condition, in fact, tells me that u dagger must be equal to the inverse of u. So I can put u to the minus 1 here, but u to the minus 1, I just changed the sign in that exponent. So as a consequence, I learn that my generators are Hermitian. Okay, great. In fact, I told you that before. Remember, we put the i's in the right places because we said in quantum mechanics, unitary transformations are the ones that are relevant. And the reason why those are the ones that are relevant is that the magnitude of our wave vector tells us the probability that something will happen. So we normally normalize that to 1. And if we performed any transformation, we didn't want to mess around with that normalization. What is the transformation that will preserve that normalization? It's a unitary transformation. And then we argued that, in fact, our generators would be Hermitian for the choices of i's that we'd put in. So we've just recovered that again. So that's not a bad thing. Now let's try to figure out, well, how many of these generators are there? So if I want to build a Hermitian matrix, how can I do it? Well, one thing I could do, so what I'm going to do is I'm going to write down a bunch of matrices, and then you could add these with arbitrary real coefficients to get the most general Hermitian matrix you could think of. So at the moment, I'm trying to write down, if you like, a basis into which I could expand any Hermitian matrix. Well, what could I do? I could put noughts everywhere except at one point on the diagonal, and noughts everywhere off the diagonal. And it's quite obvious that if I transpose complex conjugate that, I get that back again. How many of these are there? Well, there's d of them, right? Because I could put that 1 in any one of d diagonal positions. So there's d of those people. Then we've got something like this. So let's call this column I and column j. So over here we have row I and row j. I could decide to put a 1 over there and a 1 over there. if I take the complex conjugate transpose of that, I get that back again. How many of these are there? Well, we did this counting problem before. To choose where I'm going to put a 1, I can choose first my I index. There's any one of D choices for the choice of I. When I choose J, I can choose anything except the value that I've got for I. So there's a total of D minus 1 choices for J. And then finally, if I took this as my answer, I would be overcounting because I've counted that one and that one as independent. So I need to now divide by a factor of 2. So that's how many matrices there are of that form. And there's one more type of structure we could have, which looks like this. So there we've got the I, the J, the I, the J. And here we put an I, and sitting over here we put a minus I. You can see if I transpose complex conjugate that, once again, it comes back to its form, so it's Hermitian. How many of these are there? Well, this is exactly the same counting problem as for these. So over here, I will also get D times D minus 1 over 2. So let me add up what is the total number of generators. Well, it's D plus D times D minus 1 over 2 plus D times D minus 1 over 2. And that just gives me D squared. So I've got a total of D squared generators for UD. And that's also equal to the number of Hermitian matrices that there are. So what would I say? I would say to specify a unitary transformation, I need to give you D squared continuous labels. Another way of saying the same thing, I would say this is a Lie group of dimension D squared. Okay. Now, that's what we get when we allow the inner product to become complex. But when we were dealing with SOD, we also considered that epsilon. So let's generalize that too. What would happen if we now require 2 invariants? So we're going to require that inner product is invariant. And we are also going to require that is invariant. Again, 2 invariants. And remember, the U, V, and W, and so on appearing here are now complex vectors. So this is what distinguishes it from the case of the SOD. Now I'm going to run through exactly the same argument as I did in the SOD case. So I'm just going to be schematic and look back to what we did for SOD. So remember, how does our transformation work? Well, step number 1, we transform UI1 goes into, let me choose another name for my vector so that it's no chance of mistaking notation. So Wi1 would go into my unitary matrix, I1, J1, Wj1. The J1 index is repeated, so that's summed. So that's the transformation that I perform. What happens to my invariant? Well, that's the next thing we have to ask ourselves. Epsilon I1 up to ID. Wi1, YID would become, I need to transform each of these vectors. So it would become epsilon J1, J2 up to JD. Now for each of these vectors, I would get a factor of U. So I would have U, J1, I1, U, J2, I2, all the way up to U, JD, ID. And now I contract with my vectors again. So I would have my Wi1, my YID. Is everybody happy with that transformation law? Anybody want me to explain again how we got there? I will with pleasure. Okay. So that's where we land up. And now we make exactly the same argument as yesterday, which is to say, hang on, epsilon j1, j2, up to jd of u j1, I1, u j2, I2, up to u jd, id. What is this thing equal to? Well, it's an antisymmetric tensor. Yesterday we swapped two indices, and we saw, for example, if we swap I1 and I2, this thing is antisymmetric. So it will be proportional to epsilon I1, I2, up to ID. And using exactly the same argument as we did yesterday, we can argue that this coefficient of proportionality is just the determinant of U. So now what we learn is if we have both of these invariants, okay, for that to be invariant, we need to look at unitary matrices. For this to be invariant, we are forced to have determinant equal to 1. So we're going to impose both of those conditions and see what group we get. Okay? So let me maybe now just clean this. So this statement implies we are dealing with unitary matrices, and this statement implies the determinant of our matrix is equal to 1. Now, yesterday we started with OD, and when we wanted to say that we were dealing with determinant matrices with determinant equal to 1, we appended an S. We said the S stood for special, and the subset that we were considering that was special, they were special because they had a determinant equal to 1. In exactly the same way, we started off with UD. We are again going to consider matrices with determinant equal to 1, so we again append an S. We are now talking about the group SUD. Okay. So what are we going to do? Well, we're going to do what we did for every single other example. We're going to ask ourselves, what do the generators look like? Now, we've just argued that if these are going to be unitary matrices, that implies that our generators are Hermitian. So we're going to have Hermitian generators. So unitary implies Hermitian generators. Okay, that's fine. What does determinant U equal to 1 imply? What does det U equal to 1 imply? Now, I just want to remind you, okay, because this is going to be different to the analysis before. When we did OD and SOD, if you look back, they had the same generators. And in fact, we were able to argue that OD has got two disconnected components, and using the generators, we could only get hold of that component that was connected to the identity. So if I just gave you the generators, you wouldn't be able to tell if we were dealing with OD and SOD. So your natural guess at this stage might be, well, we're not going to get a condition on our generators. I mean, that's what we saw for OD and SOD. They had the same generators. Imposing that the determinant was equal to 1 had no implication at the level of the generators. Are we going to get some implication now? Well, let's see. Our generators are Hermitian. That means that I can diagonalize them. So my group element looks like e to the I alpha t. And let me imagine now I have diagonalized t, and I'm going to work in the basis in which t is diagonal. I can do that because when I calculate a determinant, it doesn't matter in which basis I calculate it. So I'm going to choose the easiest one, which is the basis in which t is diagonal. That's the basis I'm going to use. So let's denote t. It's got eigenvalues lambda 1, lambda 2, all the way up to lambda d. And if you plug that matrix into that exponential form, you can easily check that we get e to the I alpha lambda 1, e to the I alpha lambda 2, all the way up to e to the I alpha lambda d. So to get here, I use that. And the other thing that I use is, if I've got an exponential of a matrix, it's defined by its power series expansion. So I power series expand the exponential, and everywhere where I see a t, I plug that in. Then I look at the series that I'm generating, and I will notice that I'm actually generating these series. So I've summed them up now. And now I want to take the determinant. Okay, so let me be explicit. There are noughts off the diagonal. If I want to take the determinant of a diagonal matrix, what is that equal to? Product of diagonal elements, right? So let's take that product. The det of e to the I alpha t will be equal to, well, it'll be e to the I alpha lambda 1 times e to the I alpha lambda 2 times, and then we're going to keep going until we get e to the I alpha lambda d. But if I've got e to the a times e to the b, that's e to the a plus b. So I can write this as e to the sum of all of those guys. So this is e to the I alpha times by the sum from I is equal to 1 to d of lambda I. But that sum from I is equal to 1 to d is just the trace of t. So this is just e to the I alpha trace of t. And I've said that I want to consider those set of matrices which have determinant of u equal to 1. So I want to set this equal to 1. Well, e to the naught is equal to 1. So my condition now that I get is what this implies. This implies the generators are traceless. Okay? So we've learned that we have to impose an extra condition. To get the generators of UD, we only had to take Hermitian matrices. To get the generators of SOD, we have to take Hermitian and traceless. How was that going to affect our previous counting of the generators? Well, is that traceless? Sure, that's traceless. There's just noughts down the diagonal. Is that traceless? Yes, that's traceless. There's just noughts down the diagonal. Is that traceless? Nope. So I'm going to have to modify these. How will I modify them? Well, it turns out I can no longer construct D-independent generators. I can only construct D-1 independent generators. And those you could take, if you wanted to, you could take those D-1 independent generators to have the following form. I could put a 1 in the first position, and then I could start filling diagonal elements with noughts. Then I can put 1 minus 1, and I can keep filling with noughts. If I do that, clearly the trace is 0 because 1 minus 1 is naught. So how many choices do I have? Well, I stick a 1 into the first position, and then I'm going to stick a minus 1 into one of the remaining positions. How many remaining positions are there? D minus 1. So in actual fact, this is pretty interesting. We've had an extra condition imposed. And in fact, this extra condition for the case of the unitary group has played a role, even at the level of the Lie algebra. So the dimension of UD is D squared. The dimension of SUD is D squared minus 1. Okay? So I'll just summarize that. Dimension of UD. So what do we mean with the dimension of UD? This is how many labels we need to specify the transformation. This is also equal to the number of generators that we have in our Lie algebra. This is equal to D squared. And the dimension of SUD is equal to D squared minus 1. Okay, good. Now, in actual fact, we can make a tiny connection to physics. And the reason for that is, let's look at these invariants. Well, if you look at this invariant, what does invariant number 1 look like? It looks like a sum from I is equal to 1 to 3 of, now I'm going to write it as a psi I star. This is how we build mesons in nature. We combine quarks with anti-quarks. And we know from color symmetry in QCD, we know that in fact we have confinement, so we have to always build colorless states. So we must build states that are invariant under color transformations. Well, this looks like a meson. How many quarks are there in a baryon? 3. So the second invariant that we would have would be epsilon ijk, and now we bind together 3 quarks, and we can do it in this antisymmetric way. So if these are the invariants, what group are we talking about? SU3. So remember I said we wanted to turn this question on its head, and sometimes it would be useful. Here's the case where it's useful. If somebody came into your office and they said, we've been able to do high-energy experiments on a proton, and we found out that there are 7 quarks in a proton, what group would they be dealing with? SU7, right? Because you'd have to have another invariant of that type. And so just by asking people to go off and do experiments and see how many states are there bound in this thing, plus the very strong requirement that you're going to get a state that's invariant under the symmetry, that's enough to tell you a lot about the dynamics. Okay. So now you know what OD are, and SOD, and UD, and SUD. Now I want to do something which I hope won't be too boring. It's maybe now a little bit more technical, but at some point we have to do some of this stuff. And I'm going to prove 2 lemmas with you. I would say that these lemmas are maybe the most important lemmas that you could learn in group theory. Just about all of the results that you're going to use subsequently follow directly from these lemmas. One very interesting recent application of group theory has been to finding fuzzy spaces in string theory. So the idea is that perhaps string theory modifies the way that we look at the geometry of space-time. And the most powerful tool that has been applied to get hold of these spaces are precisely the lemmas that I'm going to show you now. So they go under the name of Schur's lemmas, and everything just about in group theory follows from these lemmas. Okay, so let's write down the first lemma, and I'll be careful to word it nicely. So the first Schur lemma. Says the following. Any matrix which commutes with all of the matrices in an, what do you think that IREP stands for? Irreducible representation. Okay, I'm just going to write IREP. When you read papers, you'll see people using that word. They mean irreducible representation. So any matrix which, so maybe I'll just put that translation down. So IREP equals irreducible representation. So what does irreducible mean again? We can't block diagonalize it, right? So we're talking about guys that we can't block diagonalize. Any matrix which commutes with all of the matrices in an irreducible representation must be a multiple of the identity matrix. So what do we mean? Well, so if what gamma is an IREP, and we also know B gamma of t is equal to gamma of t b, then in fact, and we know that this is true for all elements of the group, then this would mean that B is proportional to the identity matrix. So there's just some number that multiplies in there. Okay? That's the first Schur lemma. Extremely important result, and happily very easy to prove. So let's see why this is easy to prove. We're going to use the following piece of information. So let's see if I can make this clear. This is the only thing that we've really got in our back of our minds when we're proving both of Schur's lemmas. And I think it's quite a simple idea. So we've got a matrix which is, if we are in a reducible rep, we've got a matrix structure that looks like this. Gamma of Ti is equal to, and now this thing is block diagonal. So we've got maybe representation 1 of Ti, representation 2 of Ti, representation 3, and noughts off the diagonal. And so this thing keeps going. If I act with this matrix on any vector in my space, so let me imagine that I'm now acting on a vector. So gamma of T is going to act on some state, some ket V. So I'm going to write V explicitly now. So here is my column vector. When this first matrix acts, it may shuffle these first entries amongst each other. So it may shuffle those first entries amongst each other. But one thing that it will not do, this matrix, because it's block diagonal, is not able to mix elements from these different bands. So if I act with this matrix on this vector, these entries do not mix. So let's say I switched on some entry over here and these were all noughts. I could act with all of the elements of the group and I would never be able to switch any of these elements on. I would just shuffle maybe these elements amongst each other. Is that clear? Okay, if you don't believe me, write down a couple of examples and try to act on a vector and see if that's true or not. Okay, now let's try to see why is Schur's lemma true. Well, we're going to start off, so let's prove the first lemma. We're going to start off and let's say that you give me this matrix B. What I'm going to do is I'm going to calculate the eigenvalues of B. So let's say that I'm only smart enough to calculate one eigenvector. So I calculate that one. And I get B acting on, let's say, lambda. Gives me lambda onto lambda. So I found that eigenvalue. And what I'm going to do is, now, I'm just going to take this single eigenvalue and I'm going to say, split the vector space into two pieces. So let's split our vector space into two sets. Those that belong to the space, I should say subspace, spanned by eigenvectors of B with eigenvalue equal to lambda. Okay? So that's going to be a subspace. So I'm thinking some of these eigenvectors of B will have eigenvalue lambda. Maybe it's just one. Maybe it's a couple of eigenvectors. But I'm going to say, take all of those eigenvectors, and those will span a subspace. And then I've got the rest of the space, so I've split it into two. So that's the one part, and then into here I include the rest of the space. Now my logic is going to be the following. I'm going to try to show, in fact, that this is so big that it is the whole space. If this is the whole space, that means every single vector has got eigenvalue lambda. But the only matrix that has every single eigenvector with the same eigenvalue is a multiple of the unit matrix. So that's the logic of the proof. Anybody want me to repeat that logic? Okay. So now let's take a look. Let's see how can we prove this. Well, let's now use Schur's lemma. We know the following. So we act with, so let's take gamma of t, b, and we're going to let it act on this eigenvector. And we know that this will be equal to b gamma of t acting on this eigenvector. Okay? When b acts on lambda, what do I get? Lambda. So this is lambda times by gamma of t lambda is equal to b times by gamma of t lambda. Okay? So what I'm now saying is, if I let b act on gamma of t times lambda, in fact, the gamma of t times lambda is an eigenvector with eigenvalue lambda. But what I've said is, my representation is irreducible. It can't be written in this form. In other words, I can't have components of vectors that don't mix with the rest of the vector. So if I now let t run over the whole group, because my rep is not of this form, all of these components will mix. So as I let t range over any vector, this vector over here has to span the entire space. Is that clear? Should I say it again? Okay? So what I'm saying is the following. This is not what we've got, right? So we said in our statement of Schur's lemma, we said that we have an irreducible representation. Okay? If we have an irreducible representation, we don't have this. Okay? We do not have that. If we did have this, what would we have? I would be able to switch on just one element of the vector here, and I wouldn't be able to switch on the other elements, right? I don't have this. If I've just switched on one element of the vector, I will be able to switch on all other elements by acting with matrices from the group. Everyone happy with that? So as I let gamma of t vary when it's acting on lambda, it doesn't matter what initial lambda I started with, this vector will span the whole space. So what that means is you can plug in any vector from the space into here, and they will all have eigenvalue lambda. So what I've been able to show is every single vector in the space has eigenvalue lambda. The only matrix with all of its eigenvalues equal to the same number is just a multiple of the identity. Everyone happy with that? Anyone who's still not quite sure? If you feel shy, come and talk to me during tea time. Okay? This is a real important result. A huge number of things follow from this, so I'd really suggest that you master this. This is important if you want to understand group theory. Okay, so that was the first of Schur's lemmas. He's got a second one. But before we get to it, I want to see if we can put some, give ourselves some intuition about this result. What was our original problem? Well, our original problem was we wanted to find a label for something like, say, an electron. And what we wanted to make sure that that label wouldn't change under a transformation. Okay? So what was our state? Well, our initial electron state may have been psi. And then what I wanted to do is I wanted to act on that initial state with gamma of t, and I wanted all of these different states to have the same eigenvalue. That's what I said was a good label. And what did I say was a good label? Well, I said O hat, which was equal to the Hamiltonian squared minus p dot p. And now I'm dropping certain factors of c. We said that this was going to be a good label, right? Okay. Now, if this is a good label, it means that all of these states will have the same eigenvalue of O hat. And that means that when I act with O hat on gamma of t psi, so let's say that O hat acting on psi was equal to m squared acting on psi. Then if I act with O hat gamma of t on psi, I still want this to be equal to m squared gamma of t psi. This is just m squared times by psi, so I can write that as gamma of t O hat psi. So if I now compare that to that, I'm getting something that looks very similar to this, which appears in the statement of Schur's lemma. And what I also want, I would like O hat acting on any electron wave function to give me m squared. So I want O hat to be proportional to the identity. Well, if I want O hat to be proportional to the identity, and I know that that's true, then I think it's very natural to say the electron must be an irreducible representation. So it now makes sense to identify particles in the theory with irreducible representations of the group of transformations that we're looking at. And we would actually take, in fact, what is our symmetry group? Lorentz symmetry, right? So our task would be to take a look at the Lorentz group and to take a look at all of the irreducible representations of the Lorentz group. And this should now be a prediction. We should be able to see these particles in nature. So now you can see we're getting closer to being able to answer the original question that we asked. Now let's take a look at Schur's second lemma. Okay, and you know what? I think I'm not going to prove this one with you. Unless you want to see the proof. Is it instructive to see the proof? This proof is a bit longer. Maybe I'll leave the proof of this, but we'll prove some other things which are important. Okay, so let's take a look at the second lemma. And what the second of Schur's lemmas says is the following. It says, now this is a statement about two irreducible representations. So we consider two irreducible reps, so irreps. Consider two irreps, and they are inequivalent. So, irreducible, can't make them block diagonal. Inequivalent, they are not related by similarity transform. So we know what we're talking about. And we're going to call them gamma of t and gamma prime of t. So those are the two representations, and they are of dimension b and d prime, respectively. Okay? If we can find a d by d matrix such that gamma of Ta is equal to a gamma prime of t, then A is the zero matrix. So that's the second of his lemmas. And as I said before, these are real important. If you wanted to prove this, the reason why it gets a little bit tedious is that you have to consider three cases. Well, that's the proof that I know. And the three cases correspond to taking d less than d prime, d greater than d prime, or d equal to d prime. Okay? And I guess if you look at any decent group theory book, they will go through the proof. The basic idea, however, is just this one. It's just using that idea again. So as long as you understood that, it should be easy to prove, well, possible to prove the lemma. Okay. So we're not going to prove that, but we will prove a consequence following from Schur's lemmas, and this maybe is the most important consequence following, and it's called the fundamental orthogonality relation. So let's take a look at that. by proving the fundamental orthogonality relation, we're going to be able to make contact with certain things you know in quantum mechanics about adding angular momenta, and we'll be able to actually derive some constraints on the number of irreducible representations a group has, and do all sorts of interesting things like that. So now let's prove the fundamental orthogonality relation. Okay. So I'm going to ask you to consider the following matrix. Consider B, A, B, R, S, I, J, and this is defined to be equal to a sum over all of the group elements, gamma A of T, IR gamma B of T to the minus 1 Sj. This is a busy formula, so let's think about it. So there's a couple of things going on here. So first of all, you can see I've got these labels A and B sitting here. So there's A and B. Here they are on this side of the equation. There they are on this side of the equation. What A and B label are the representation that we're looking at. So A and B label the irrep we're looking at. So you form this matrix by taking the matrix which represents T in representation A, and you multiply by the matrix which represents T to the minus 1 in representation B. Now, what are I and R? On this side of the equation, I and R are matrix indices for the matrix representing T in representation A. Everyone happy with that? Now notice that on this side of the equation, I plays the role of a matrix index, but R is labeling my matrix. So it's playing a different role on both sides of the equation. Please notice that. Here I would specify I and R to get one of these matrix elements. Here to specify a matrix, I would specify A, B, R, and S. And to specify a matrix element of this matrix, I would specify I and J. So R is playing a really different role here to what it's playing here. And that's the same as these matrix indices, the S and the J. So J plays the role of a matrix index, but not S. S is a label for this matrix that I'm considering. Are there any questions on the role of the indices in that equation? Okay, so it might take a bit of getting used to, but think about it. And now we've got Schur's lemma. And
what the dimensions are on either side?
Sure. Okay. So what we've got sitting on this side, okay, this thing, let's say, has got dimension dA. This thing may, in fact, have dimension dB. So when we take a look at this matrix, what's the dimension of this matrix going to be? Well, how many rows are there? dA of them. How many columns are there? dB of them. So this would be a dA times dB dimensional matrix. Okay? How many matrices would there be? Well, obviously it's related to the number of representations you could consider and to the dimensions of those reps. Okay, so there's quite a few of these matrices. We're just looking at one of them. Okay. Now, what is Schur's lemma a statement about? It's a statement about how things commute, right? So we're saying gamma of T A is equal to an A, a gamma prime of T. Yes, Rocco? A is not a square matrix if D is not equal to D prime.
Okay, but so you mean the D by D matrix just above it is D by D prime, or do you mean D by D prime?
I mean D by D prime, thank you. You're quite right. Yep. Now let me... Yeah, D by D prime. Okay. So Schur's lemma is telling us about how things commute. So it just seems natural that we should try to construct a commutator now. So let's try to do that. Let's take gamma A of T tilde, and let me get these indices straight. This is IK, so I am indicating the matrix indices explicitly, and we're going to multiply these matrices. And this multiplies into B, A, B, more labels, R, S, and K, J. So the index K is summed. I'm performing a matrix multiplication here. Now, to perform this matrix multiplication, I am going to plug in my explicit definition for B. So this will be a sum. T, an element of G. Gamma A, T tilde. Let's say I, K. Gamma A of T. Now I want K, R. Gamma B of T to the minus 1, Sj. But you see, this is a group, so I know what the product of these two will be. This is just going to be, this is a sum, T, an element of G, gamma A, T tilde T, I, R. So I've done that matrix multiplication. Gamma B, T to the minus 1, Sj. And now I'm going to relabel my group sum. Like I did, we used that for a previous result. Let me just try to remember which one it was. Okay, I can't remember what result it was. But so we've got this. We're going to now say T bar is equal to T tilde T. And I would now like to change my sum into a sum over T bar. So over here, now I want to sum over T bar is an element of G. Now, notice the following. How many values of T did I sum over? Order of the group, right? How many values of T bar will I sum over here? Order of the group. Okay? And the other fact that I'm using is, if I fix T tilde, okay, then if I start off with T1 not equal to T2, then T bar 1, which is just T tilde T1, will not be equal to T tilde T2. Just multiply this by T tilde, which is equal to T bar 2. So that means this sum over here had to run over G distinct values. This sum over here has to run over G distinct values. So they must both just be sums over the group. I call this, I think this is called the right invariance of the group sum. Okay? And that's what we're using here, right invariance of the group sum. Gamma A of T bar, IR, gamma B. Now, what is T to the minus 1 equal to? Well, from this equation over here, I learned that T is equal to T bar, T tilde to the minus 1. So T to the minus 1, I should swap the factors and invert each factor. So I would get T tilde, T bar to the minus 1. What? Did I do that correctly? Yes. So there's T tilde. T is equal to T bar. So T to the minus 1, which appears here. Now, I don't like that result. I want T bar to the minus 1 T tilde. So T bar is equal to T tilde T. T bar is equal to T tilde T. So this tells me T would be equal to T tilde to the minus 1 T bar. Okay, so that's my mistake. So if I look at what is T to the minus 1 equal to, this will be T bar to the minus 1 T tilde. Okay? Everyone happy with that? So I'm now going to plug this in for T to the minus 1. This is t bar to the minus 1 t tilde. And now I guess there's an important comment that I should make, and it's the following. In moving from this line to this line, I actually used the invariance of the group sum under this change of variables. When you are working out the representation theory of groups, 99% of the theorems that you will prove use this invariance. For a finite group, this invariance is trivial. If you're dealing with Lie groups, you of course don't have a discrete sum over elements, you have an integral over the group. Whenever you can show that your integration measure has this property, you will have exactly the same representation theory for your Lie group as you do for your finite group. It turns out for the Lie groups that we've looked at so far, so OD, SOD, UD, SUD, they do have this property. Okay, so this is the property that I'm using. I could change the sum from t bar to t, and the actual sum would be invariant. If I was doing an integral, I would say the measure of the integral would be invariant under that transformation. So the measure would be the same whether I integrate over t or whether I integrate over t bar. That's a crucial step. And it's when you've got that being satisfied that your representation theory for your Lie group will be exactly the same as the representation theory for your finite group. Okay, so what is this now equal to? Well, it's a sum over t bar as an element of G, gamma A of t bar IR. And now I can expand that out if I like, because I know this is again a group rep. So this is t bar to the minus 1. This should have been Sj. Sk gamma B of t tilde Kj. Now I want to compare this line with this line. And those are the only two lines that I want to keep. Let's put that down and see what we get. Maybe I'll put it here. So looking at the top line, we've got gamma A of t tilde Ik acting on B, A, B, Rs, Kj is equal to, and on the bottom line, this thing that is sitting here, I'm now going to look again at the definition of B and realize that that is just BAB. Okay, let's just get these indices straight. So the RS came from RS, the middle two indices. So here the middle two indices are again RS. And the matrix indices are IK times by gamma B of t tilde Kj. So look what we've got. This is one irrep. This is another irrep, and they're related by this matrix. But look at Schur's lemma. This is the content of Schur's lemma. Irrep, irrep, matrix, 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 second irrep, second irrep. So we were told that A would be naught if the two representations were not the same, right? Okay, that tells me something. So what it's telling me is BAB RS, let's say Kj. So this is going to be naught if A is not equal to B. That we know, just straight from Schur's lemma. But if A is equal to B, then according to Schur's first lemma, B has to be proportional to the identity. So we want a delta Kj. And I have got no idea about the dependence on R and S. So let me summarize this in an unknown constant that I will call C as a function of R and S. And I'd now like to figure out what C is. there's a nice, easy way to figure out what C is. We're just going to take the trace of B and see what we'll end up getting. So let's do that now. What we want to calculate the trace of B, A, R, S. Now, I've been telling you everywhere that whenever you see a repeated index, you should sum. For this one equation, do not sum over A. So let me... No sum on A. So let's see why this is a good thing to look at. Well, let's take a look. If we take the trace from here, we're going to get CRS. And when this delta Kj, that's just a unit matrix, so we're just going to be adding up all of the ones on the diagonal. So we're going to get the dimension of representation, A. And let's now calculate this thing again, but using our definition of BAB. So the two reps are the same. So I'm going to have, again, a sum over T is an element of G. Okay, and I've got a gamma A of T. And I'll put indices on in a moment. And a gamma A of T to the minus 1. When I take the trace, I'm setting K equal to J and summing. So if I take a look at this, there's the ij. I must set this first index equal to that index. Okay? So if this is an I, that must be an I. And RS are now the inside indices. So RS are the inside indices. Okay, everyone happy with that? So let's take a look and see what this is. This is equal to, well, and over here, of course, again, so let me just, we're summing on I. I is repeated, we sum on I, no sum on A. Now, if we sum on I, using the fact that this is a representation of the group, we just get sum. T is an element of G, gamma A, T. Okay, so I'll put it down. So we have T to the minus 1T, SR, which is a sum T element of G. The identity, SR. Now, this sum on T as an element of G, well, nothing depends on T anymore. The T's have disappeared. So we're just going to get a 1 for each time that we sum. So we're going to get G, the order of the group, and we've got the identity matrix, delta RS. So now we compare this to this, and what we learn is we learn CRS dA is equal to G delta RS. And what that tells us is now we've got a formula for BAB. So I'll write that formula out in full glory. So where is BAB? It's sitting over there. So we've got a sum over T, which is an element of G. Gamma ATIR, ATIR, gamma B, T to the minus 1, SJ. So what is this equal to? Well, we've got a delta AB, we've got a delta RS, we've got a delta IJ, and we've got a G divided by, where was it? dA. So there's our result. Now, I should come clean about one thing. So what I did do is, over here, so I glibly told you to replace gamma A of E equal to delta RS. One of the things that you might ask me is, is the matrix representing the identity always the unit matrix? Okay, the answer is yes, it is always the unit matrix. And the way to see that is, well, if we take gamma of E, this is now for any matrix rep, times by gamma of E, that's equal to gamma of E because the identity composes with the identity to give you 1. So if I pull this over to this side, I learn that gamma of E into gamma of E minus the unit matrix is equal to 0. But that guy's invertible, okay, because the inverse of every element must appear in the group. If that guy's invertible, the only solution to this equation is that gamma of E is equal to the identity matrix. Okay? So I used that fact. So that's our result. This is called the fundamental orthogonality relation. And it can be put to really, really good use. So let's put this down. This is the fundamental orthogonality relation. Okay, now, let's check. What we're interested in, of course, is continuous groups, something like Lie groups. Is there an analogous result for Lie groups? Well, yes, there will be an analogous result for Lie groups when we can relabel our sum, which will now be an integral in this way, and the measure will be invariant. For those of you who know something about groups, if your Lie group is compact, that will always be the case. So that's been proved carefully. But there's a slight change to this result. And the reason why there's a slight change is it comes in with this value of G. Where did this value of G come in? It came from summing over all T, which is an element of G. So when we're talking about a finite group, we usually have this sum normalized to G, the number of elements in the group. Now, when you think about a Lie group, there's an infinite number of elements. So that would be a stupid normalization. So the normalization that we have in the case of a Lie group, we say that the sum over all group elements over the group manifold is usually normalized to 1. That's a much better normalization to choose. And with that normalization, the fundamental orthogonality relation becomes the following. This is how we write it. We say that, so we're going to replace that sum by an integral over the group, gamma A of T, I R, gamma B of T, so this is to the minus 1, Sj, dt is equal to delta AB, delta Rs, delta Ij over dA. I just mentioned that because you guys will probably see things in the context of Lie groups, so I wanted you to know that the result carries over for that. There's quite a bit of work that goes into defining exactly what you mean by that integral and looking at the various symmetries that that measure would have. So I don't want to do that here. Okay. One more thing that I do want to do today is I'd like to show you that if we're dealing with a finite group, and in fact this is also true for groups, Lie groups, which you can change the measure in this way, then you can prove that every single representation that you have is equivalent to a unitary representation. And the reason why that's a useful result is that from now on we're going to restrict ourselves to unitary representations, and we know that we're still being absolutely general because every rep is equivalent to a unitary rep. Okay, so how do we prove that? Well, we'll do it as follows. Actually, before we start on that, let me just ask, does anybody have any questions on the fundamental orthogonality relation? Yes, Noreen. Okay. You know what? I hope that this will satisfy you. What we're going to do tomorrow is we're going to look at characters of SO3. So you know what characters are. We're going to look at them for SO3. And we're going to use that formula. One of the things that formula will allow us to do is it will allow us to work out what is the irreducible representation content of a product of two other representations. And what we'll be able to relate that to, in quantum mechanics, you probably went through the exercise of taking a particle of spin J1 and coupling it to a particle with spin J2 and figuring out what were the possible allowed angular momenta. Okay? So we'll see, for example, statements like that can be read off of that fundamental orthogonality relation. Okay? So I'm going to ask you to hold off with that question till then. I am going to try to give you some sort of physical interpretation in various cases. I don't know, is there anyone sitting in the audience who's got a nice interpretation for fundamental orthogonality relation? Physical interpretation? Clifford, maybe? Yeah. Okay. So Noreen, tomorrow I promise we'll do angular momentum. And that's the best I can do for you now.
The second thing, when we calculate the dA, or when the dA came into our calculation, we could have as well as taken the trace of B and then index BB, so it would be dB there. And I think there's no reason for them to be the same. Actually, the formula tells us that they are the same. But can you just remind me again? Okay, now, so the gamma A and gamma B are actually as well.
Yes. So the gamma A and gamma B, yes, that's true. Those are irreducible representations.
And they both must have the same dimension?
Well, okay, on this side, okay, A is equal to B. So in other words, if you consider two different irreducible representations, you just get naught. Okay? Well, it follows from this formula, right? Because the only time this is non-zero is when we've got the same rep here as we have here. Okay? In fact, you could plug in two irreducible representations that have the same dimension, and as long as they were different irreducible representations, you'd still get naught. That's what that formula tells you. Okay? Does that answer your question? Good. Okay. So now let's show that every representation is equivalent to a unitary rep. So let's imagine that we start off, and I'm going to prove it like this. We're going to start off with some rep, and then I'm going to show you how to get a unitary rep from it. So let's say we've got a matrix representation of the group, so gamma of t. This is going to act on a ket. And the ket that I'm going to get from acting with gamma of t on that ket, I am going to call TV. So that's the ket that I get. Now, I haven't told you how to calculate inner products on this space. I'm going to use an interesting inner product. The inner product that I'm going to use is this one. So here we've got a G. V prime G is equal to 1 over G sum T is an element of G, gamma of T, V, gamma of T, V prime. So let's make sure we know what we're saying here. So this inner product here is the usual inner product. I've just taken my vector. To go from a ket to a bra, I take the transpose and I complex conjugate. And then I would contract them the way I contract vectors usually to get an inner product. So use the rules for contracting. What is it? So this would be a row. So this would be a 1 by D into a D by 1 matrix. Okay? So use those usual rows. That's the inner product that I mean on this side. I'm now summing over all elements in the group. I'm normalizing with 1 over the order of the group. And I'm defining this to be equal to an inner product. So this subscript G is just to remind you that when you compose these two vectors, you don't do it using the usual inner product. This is a new definition of an inner product. And now what I would like to show you is with this inner product, this representation is unitary. So how do I do that? Well, what do I mean when I say I've got a unitary representation? I mean the inner product is preserved by the transformation. So I'm going to transform both V and V prime, and I'm going to transform them like this. I'm going to take an element of the group, and I'm going to act on V to give me T tilde V, and I'm going to act on V prime to give me T tilde V prime. And now I'm going to take the inner product of t tilde v with t tilde v prime using this inner product. And if I can show that the inner product hasn't changed, so I get the same thing as I would have gotten if I took the inner product of v with v prime, then I've got a unitary rep. The inner product was preserved. So let's see how we're going to do that. So we want t tilde v, g, t tilde v prime. So what is this equal to? Well, this is... okay, so sorry, I somehow changed notation somewhere there. So that wasn't good. So that's a bit better. So this will be equal to 1 over g, a sum on t as an element of g. Now we want t on t tilde v, and we want t on t tilde v prime. Okay? But this I can write as 1 over g, sum on t as an element of g, v, gamma dagger, t tilde, gamma of t tilde on v prime. And now I'm going to again introduce a new integration variable. I'm going to call t bar is equal to t tilde. Then what does this sum become? It becomes 1 over g, sum on t bar is an element of g, v gamma dagger of t bar, gamma of t bar, v prime. And what am I using? I'm again using the fact that the sum is invariant under that change of variables. That exact same change of variables. That comes up everywhere in representation theory. And this is equal to 1 over g, sum over t bar element of g, t bar v, t bar v prime. But that's the inner product that we would have gotten if we had just taken the inner product here of v with v prime. Okay? This is exactly the same as that. That there is exactly the same as that. That means that the inner product is invariant, so I've got a unitary representation. Any questions on that? Okay, is everyone happy with that result? Do not feel shy to ask questions. Rocco, you happy with that?
No, I'm just wondering if those steps that you know really necessary.
Well, you know what? I mean, you might have been unhappy what I was doing here if I was manipulating the vectors. But certainly here I'm talking about a group element. So I'm now summing. This is a group element. And I know that when I make the change in the sum here, certainly that's something you can think about. So that's why I put that in. Okay? Okay, so that means certainly this inner product is unitary. So if I use this inner product to calculate matrix elements, I would land up with a bunch of unitary matrices. And what did I use again to prove this? Okay, so I know I keep stressing this point, but it's because it's important. I used the invariance of the sum under that change of variables. If your Lie group is invariant under that change of variables, every representation of your Lie group will also be equivalent to a unitary representation. Okay? So that's what's driving it. Okay, and the reason why I wanted to show that every rep is equivalent to a unitary rep is because I now want to write down my fundamental orthogonality relations for a unitary rep, and I'm not losing any generality when I do that. So that's why we did that exercise. So let's now put that down. Now, if I'm in a unitary rep, the inverse of a matrix is equal to the complex conjugate transpose, right? So the way that I rewrite this condition, I say I've got a sum t as an element of G. So gamma A stays exactly the same. Now, instead of using an inverse there, I will complex conjugate and take the transpose. And that will be equal to delta AB, delta RS, delta IJ, G over dA. And this is the form that we're going to use it in. And as far as the integral goes, so I'm just going to change this one as it is. So this is the form you'll often see it written in. This is actually under the assumption of a unitary representation. And in fact, we now have enough to prove that the list of irreducible representations only has a finite number of entries. So let's prove that now. A finite group, a group of finite order, will only have a finite number of inequivalent, irreducible representations. So let's write that down. Okay, so we're going to define a vector, and the vector looks like this. It's got three labels, I, R, and A, and these are the elements of it. Gamma A of T1, IR. Gamma A of T2, IR. And we keep going till we get to gamma A of T G IR. How many elements are there in this matrix? How many entries are there in this vector? G, the order of the group, right? So this is a G-dimensional vector. Everyone happy with that? How many of these vectors are there? Well, how many different values can A take? R. Okay? So A can range from 1 to R. And how many values can I and R take? Well, that's the number of matrix elements inside the matrix, right? So I and R can take a total of dA squared values, where dA is the dimension of the representation. Let's go through that counting again. A labels the irreducible representation that you're looking at. For a specific irreducible representation, you can look at any matrix element when you specify I and R. So if representation A has got dimension dA, the number of matrix elements that we have is dA squared. I can take any value from 1 to dA, and R can take any value from 1 to dA. So if I want to work out the total number of vectors, I have to sum from A is equal to 1 to R of dA squared. Okay? So this is equal to the number of vectors. dA is equal to the dimension of representation A, and it's a G-dimensional vector. Sorry? R? I and R would label a specific matrix element inside this matrix rep. So to count the values that I and R can take on, I must count the number of matrix elements. Right? So I can be 1, 2, up to dA. R can be 1, 2, up to dA. So the total number of values that I and R can take on is dA squared. You happy with that, Noreen?
Yeah, I don't understand why it comes up in the sum on the right.
Okay, well, let's take a look. When you want to specify a vector, okay, how many choices do you have? You have to specify A. Once you've specified a particular representation, you have to specify I and R. The number of values that I and R can take on will depend on A, right? Because different reps have got different dimensions. So I need to calculate the number of values I and R can take on for each A, and then I need to sum over A. Right? Okay, let's try to count these vectors. You tell me how to count them. Maybe I'm counting them. R is equal to the number of irreducible representations. Okay, I need to sum over all values of A. Oh, okay. That's quite true. So we'll do this. Okay, is that what was worrying you? Good point. You happy now? Good. Any other questions? Okay, good. Now then, let's check some property of these vectors. So this is interesting. Let's calculate JSB onto IRA. Let's calculate what that inner product is. What is that inner product? Well, I need to take the ket vector onto the bra vector and sum. So I'm going to be summing over all t's as an element of G. Now let's put in the ket vector. So we will have gamma B complex conjugate JS of T gamma A of T IR. Everyone happy? That's the inner product of these vectors, right? So that's the element of the ket, that's the element of the bra, and then I need to sum over the vector index, which in this case is the same as the index labeling group elements. What is this equal to? This is just G over dA, delta ij, delta rs, delta ab. Okay? Any questions on that? So these vectors are orthogonal. If I have got 10-dimensional vectors, what's the biggest set of orthogonal vectors that I could have? How many at most could I choose to be orthogonal if they're 10-dimensional? 10 of them, right? If my vectors are 2-dimensional, how many vectors, 2-dimensional vectors, can I have that are orthogonal at most? 2. If my vectors are G-dimensional, how many vectors could I have in total that are orthogonal? G. So the sum from A is equal to 1 to R of dA squared has to be less than or equal to G. Okay? Now, dA has to be at least 1. It's a positive number. So at most, I can only have a finite number of terms appearing on this side of the equation, and that means that R has to be finite. So for every finite group, we must have a finite number of irreducible representations. Okay? There's an analog of this for compact Lie groups, which I think is called, it's the Peter theorem or it's the Peter-Weil theorem. And it just says that the number of irreps is countable. Okay? Are there any questions on that? Okay, so I hope you can see we've reached one of our goals now. We've been able to show that on our list of irreducible representations, we'll only have a finite number of entries. Okay? So we've managed to say something about the number of irreducible representations. Okay, if there's no more questions, this is a good place to stop for tea.